Welcome to Math 331 problem solving. This should be lecture 16. So what we're going to do today is going to be the geometry day. Right. And then there was a problem that was proposed by someone to look at. As they're not here, I will bring it back later. So let's start off with irrationality. I think I've mentioned this result, but I don't think we've done the proof yet. Have we done the proof of the square root of 2 by using geometry?
I think so.
Okay, we did do that proof with the two boxes. Okay, excellent. Did we do the proof of the square root of 3? All right, so we've done square root of 2, not to scale, was like this, where this was A and this was B. And it's very similar to the proof by descent, where you assume square root of we assume square root of 2 can be written as A over B, and it's in lowest terms. So you can assume that B is minimal. And then you show that you can always get one that's smaller. So as I remarked, somebody was giving a talk on this for the colloquium many years ago as part of 6 proofs of the irrationality of square root of 2. And immediately after the talk concluded, I mentioned here's a way to get square root of 3. What shape do you think would be useful for square root of 3? Triangle. Be more specific. What type of triangle? Equilateral triangle. So the idea is roughly like this. Again, not even closely drawn to scale. So you would have these areas here that would all be double counted. And this area here would not be counted at all. So if this whole side is A and this side is B, we will assume square root of 3 is A over B and B is the smallest. So you always want to be careful. Are you making any assumptions? And if so, are these assumptions true? If you look at square root of 3 being rational, must there be a fraction with smallest denominator? Why? Why must there be, if it's rational, why must there be some fraction with smallest denominator? What would be the contradiction if that weren't the case? So imagine that there was no fraction with smallest denominator. That would mean you would have an infinite sequence of fractions with smaller and smaller and smaller denominators. Can you have an infinite sequence with small denominators? What kind of number must B be? Whole number. It's got to be a positive integer. If there weren't a fraction with smallest denominator, you would have an infinite string. So this is essentially the descent argument, that it's got to stop at some point. So there could be multiple rationals that equal square root of 3. Choose the one with the smallest denominator. Okay, so now if we look at the area of these 3 triangles, we get 3b squared is a squared. Because we're assuming square root of 3 equals a over b, so 3 equals a squared over b squared. So let's look at this picture. Since the area of these 3 triangles equals the area of the big triangle, then these 3 parts that are double counted must exactly equal the area of the part that we're missing. So the question is, what is the dimensions of these smaller things? Well, if this whole side is A and it's B to here, and it's also B to here, how much is this side over there? 2b minus a. So this triangle is 2b minus a by 2b minus a. What about the big triangle over here? What's the dimensions of that one? You can give it to me as a subtraction problem. You do not need to do the subtraction. I will do the subtraction for you.
B minus 2 times.
Yeah, it's this whole side is b, so it's b minus twice that. So it's going to be b minus twice 2b minus a. So that will be 2a minus 3b. Now, when we do the area of a triangle is not side squared. There's a proportionality constant for an equilateral triangle. I think it involves square root of 3 and 4, something like that. Does it really matter what that proportionality constant is? No, because it's going to affect everything equally. I rescale this, I rescale this, I rescale this, and I rescale that. So we get that 3 of these is equal to 1 of this. So we get 3, and this one is essentially going to be 2b minus a squared equals 2a minus 3b squared. So the square root of 3 is going to be 2a minus 3b over 2b minus a. What do we need now to be done? We want to get a contradiction. What's our contradiction? Yes?
A over B is not the same as that.
So A over B is not the same. It shouldn't be the same. This should be smaller, right? Well, I mean, in some sense, A over B is this, because by assumption they both give us the square root of 3. So you're close. What's the contradiction?
Smaller denominator.
It's a small denominator. So we need 2b minus a to be less than b. Right? Or we need b to be less than a. Okay. We know that's true. True as the square root of 3 is greater than 1. So because the square root of 3 is greater than 1, b is less than a, so 2b minus a is less than b. And we now have a contradiction. This is a geometric proof of the irrationality of square root of 3. You can push this further. You can get square root of 6. And you can keep getting other numbers. So, I may get it slightly wrong. I apologize that it's not even closely drawn to scale. Like this. And then, so that would be my triangle there. And then over here, I think I would want to come down. This is really badly drawn. Yeah, okay. So really badly drawn, I think. Something like this, where I'm counting this again, this again, this again, this again, this again, this again, and this part over here is actually not counted twice, but counted 3 times. And then these ones over here are counted 0. So you can use this when the dust settles to get square root of 6. So 3 and 6 are 2 numbers in an interesting sequence. I'll give you the first number in the sequence, 1, 3, 6. Anybody know the next number? 10. And the next number? 15. So these are the triangle numbers. So the nth triangle number is n plus 1 over 2, or maybe it's an n minus 1 over 2. Probably a plus 1, yeah. So these are the triangle numbers. So if I keep drawing triangles like this, do you think I can show that every triangle number has an irrational square root? What do you think? How many have confidence in their professor?
It fails at some point.
It fails at some point. I like how you said it fails rather than my professor can't do this. Why does it fail? Or why do you know it fails? What are you looking at? Do you remember what he said? Do you remember where the issue is? What comes after 15? 21. What comes after 21? I'm sorry? 28. And 36. Okay, let's stop at 36, okay? This is enough to show that shit happens. Right? There is no way we should be able to show that the square root of 36 is irrational. So what this means is this method, which is working up to a certain point, must break down. So my question is, how badly does this break down? Does it work, say, whenever you expect it to have a chance? So we've mentioned Dirichlet statements for primes in arithmetic progression. So if A and B are relatively prime, there exists infinitely many primes P congruent to A mod B. So there are infinitely many primes that have a remainder of B when you divide by A. If A and B are not relatively prime, you don't expect this to hold. There aren't going to be infinitely many primes congruent to 5 mod 15. There's at most 1, 5. So Dirichlet says, as long as you're not in that stupid situation, what you expect happens. So no one has investigated this yet. This is an open problem. If people want to do this, this will be worth 4 homework problems. See how well this method works. Does it always give an irrational number when it has a chance? And understand, why the hell does it break down? It's got to break down at some point. What's going wrong with this? How far can we push this? I'd love to know. For an A plus in the class, prove the cube root of 2 is irrational. You do that and you're done. Don't even have to come to class anymore. You're welcome to, of course, and I would encourage you to. But use these geometric methods to prove the cube root of 2 is irrational. We were able to prove the square root of 5 is irrational by looking at pentagons. You might be able to do square root of 7 using septagons. So if you could do something like that, that's also worth 4 homework problems. I'm willing to give a lot for something like this. In addition to homework problems, it will almost surely get you a publication. My Erdős number is 2. If we write a paper together, that gives you an Erdős number of 3. Right? That's not bad. That would get you at the level of my children.
Wow.
So we'll see the paper that my kids and I, hey, it's not bad though. They've how many years have they had with me versus how many years you had, right? So if you look at it that way, proportionally, you're doing much better. So we will do the paper that Kim and Kayla wrote with me and some of my other Williams students a few years ago later in the semester if there's interest. It's a nice game with a lot of really surprisingly good mathematics arising. In fact, a generalization of the Catalan numbers arises in that problem. All right. Any questions on the geometry stuff here?
Wait, how do
Yes.
you get from the 3 small triangles being equal to the central triangle?
Sure. So in this one, we know that 3b squared equals a squared by squaring and multiplying. Well, what's 3b squared? 3b squared is essentially the area of these 3 triangles.
Oh, I see.
And a squared is essentially the area of the big triangle. There is that proportionality factor, but we're not going to worry about it because it hits both sides equally. So something goes wrong with this argument. And I would love to understand that further. I have deliberately not thought about this to save this for students, so I'm hoping somebody gets excited. All right. Did you guys have a problem on points on a hemisphere? Was that a homework problem to think about?
Yes.
Okay. So I really want to talk about this. I'm sorry?
I was just saying exemption problem.
Yes, no. And you absolutely want to save exemptions for stuff like this. When I was a senior at Yale, I was taking a really good mathematical physics class. I was, I think, the only undergraduate in this graduate level class. It was a tough class, but I learned a lot. There was only one homework problem I did not do. It's the only problem I ever did not do in my career as a student. There's something called the Schwartz-Christoffel formula. So in complex analysis, you learn a beautiful result. If you have any simply connected surface, there is an analytic, which is complex differentiable, infinitely complex differentiable map between that and a unit disk. you can often give an explicit version of the map, especially if you're set as a polygon or polygonal. So I think we had something like, something like this. And the homework problem was to find the explicit map to the unit disk. And it's the only time I said, I'm doing fairly well in the class. My homework average is pretty good. Most of the time, the grader for the class just Xerox solution keys from one of the students. There was a really strong graduate student, but every now and then my solutions were the ones that were Xeroxed. Wasn't worth spending the time on this problem. So absolutely agree that you should save homework exemptions for when you get problems like this. And just say, that's why I've got stuff in the bank. Or save them up in case I'm going to have a lot of work coming up. This is why they are transferable across years. And I've had some seniors who've had just very enjoyable springs. So 5 points on a sphere implies 4 on a hemisphere. I believe that was the problem, right? No matter what 5 points you choose on a sphere, there must be 4 on a hemisphere. So I really want to talk with you about how to do this. So how many of you used a homework exemption for this problem out of curiosity? Only one, okay. Wow. So when we're analyzing this, the problem is stated as 4 points on a sphere, 5 points on a sphere. What should you do first? Yes?
Do it with like 1 point, and then do 2 points.
On a sphere?
On a circle.
Go lower than a circle. This is like limbo. How low can you go? Start off with a line, right? Go as low as you can and start building up intuition. Sometimes if you go too far, the problem might degenerate to the point where it's not really useful. But let's just get in the habit. So, 1 dimension. So we have, here's 0, here's 1, here's -1. I'll draw it like this. That would be our analog of the sphere in 1 dimension. How many points do you think we need to guarantee that there is at least 1 on a half sphere?
1 point.
Yeah, I think in this one, just 1 point will be enough, right? It's got to go somewhere. So here we want, 5 points on a sphere. We want to show that 4 have to be on a hemisphere. So at 1 dimension, this problem is so broken down that it's really not that interesting. All right, let's bump up to 2 dimensions, and now we actually have a circle. So now we want to have some number of points on a half circle. So how many points do you think we want to have on a half circle?
4 and 3.
Probably 4 and 3. So given that we have 5 and 4, we're trying to figure out what it is. Maybe if 4 points, then 3 on a semicircle. That seems reasonable. So if we start off with just 1 point, it's clearly possible not to have 3 points on a semicircle. What if we have 2 points? Is it possible to have 2 points not on a semicircle?
You say 2 points not on a
Yeah.
No.
Yeah, so with 2 points, we're clearly going to have 2 points on a semicircle, no matter where you put it. Even if it's directly underneath, that will still be on the semicircle. So in some sense, if I have 2 points, I clearly will have 2 points on a semicircle. So the first interesting case is trying to do 3 points on a semicircle. So maybe for the previous problem, we should have tried to do 2 points on that version. And that would have required us to have 3 points total. So we go back to 1 dimension. If we want 2 points on our half circle, we need 3 points. And then what we'd have is first point goes there, second point goes there, and then no matter where the third point goes, we would finally have our 2. So that's probably the correct way to look at what's going on in one dimension. Question? Or?
Are the points always on the perimeter of the circle?
Yes, always on the perimeter. So, to try to make the problem interesting, we see it's not interesting to try to get 2 points on a semicircle because any 2 points are always on a semicircle. You can't be further apart. What about 3 points? Must 3 points always lie on a semicircle?
Yes.
So no matter where I choose the 3 points, I agree that it's possible that they could. But do you have to have 3 points always on a semicircle? So what figure might you want to look at?
1 on top and 2
So
like
even
an
space.
equilateral triangle.
Yes. Yes.
Yeah.
Yeah. Foreshadowing, the art of a great, well thought out lecture, right? What did we start off today doing? Equilateral triangles. This is known as priming. Right? If you take a geometric shape like that, you will always have 2 points on a semicircle, but never 3. And the problem is the angles are too great. The angle here is 120, and it's another 120, and then another 120. So then you could ask lots of interesting questions. If I choose 3 points at random on the circle, what's the probability that 3 of them lie in a semicircle? That's a nice probability question. This is not a probability class, but hey, I'm teaching probability later today. Maybe I'll give that to them. Right? So we know that 3 points is not enough, and we even have a shape. And you might be able to push this up to the sphere. And you might be able to keep up coming up with shapes like this or whatnot. We could also play other games such as, what if I want 4 points on a semicircle? How many points do I need for 4 points? And if I start varying these things, what shapes are going to be my problems? So we'll talk a little bit about that if time permits. So what about 4 points? Do you think 4 points is enough to ensure? Yes.
Can't you kind of boil it down to the lower dimensional case? Because like if you have any 2 points, and then like if you look at it from like the right angle, then it's essentially just like a line.
Okay, so I'll start off with 2 points,
Yeah.
like this.
Yeah.
So here's my first 2 points.
So
Now what do I do?
If you have like a chord between those 2 points, and if you like sort of like look at it from that chord, then it's just a line with 1 point.
But now I have to choose 2 more points.
No, so like that would boil down to the line case where you have like 1 point placed.
Okay.
And so because for the line case, for the 1-dimensional case, you only need you need 3 points, so you need 2 additional points.
But I'm saying, I need to make sure, you need to be able to tell me where's my semicircle that's going to have 3 points.
Oh, like, so if you reduce it to the 1-dimensional case where both of those points are like one-dimensional point, like if you're like looking at it from the side, so to speak.
Oh, I see, looking at it down.
Then like whatever, then like the center of the circle is the center of the line.
Okay.
Yeah.
But of course, remember, our line was not solid. Our line only had 2 points at the extremes and they were
Right,
disconnected.
but in this case it would be.
It would be connected.
Yeah.
All right, so if I look at it this way, so here's 0, here's 1, here's -1. So let's say I have 2 points both on the same side. Now I have to put down 2 more points. What if my 2 points are all down here?
Oh, I mean that like when you're projecting down from 2 dimensions to 1 dimension,
Right.
you project down such that those 2 points are like overlapping, so that they actually become 1 point in the lower dimensional case.
Oh, I see. What you're saying is
Yeah.
choose your coordinate axis like this.
Yes.
Okay, so we do it like that. And go, now, here we do have the wraparound. So now,
So you only have 1 point, and then.
so we would have a doubled point here. And I have to choose 2 more points.
But it's this kind of the same thing as.
But what if I choose my 2 points to be all the way over here? Which. Oh, what you're saying is that one point has to be within 180 degrees of one of these 2 points?
No, it's just like the method I used for like the homework problem was like, since we're working with a sphere, if you take any 2 arbitrary points, you can draw a line through them and like basically boil it down to the circle case.
Okay.
And I'm just suggesting that you can do the same thing.
So now I have to choose 2 more points. So where do those 2 points go? Yes.
I mean, I have a question. So then, when you choose the other 2 points, are you staying on the line?
You would have to choose them on the circle, and then you could project downward.
So it could be anywhere on the line.
So it could be anywhere. It could be anywhere on this line.
Because I'm a little confused, like why the line helps. For example, because if you have like another like double point, right, at like -1 here,
Right.
how does the line?
I mean, imagine these 2 points are very close to each other over here, and I choose 2 points very far away from here. So I'm happy to look at that. It's not a bad idea to try to project down to lower dimensions. I'm just not sure if this is going to work. It's a nice try.
Choose a different axis if you want.
No, I like the idea of choosing a different axis. And then I agree that one of the points, because things might wrap around a little bit, but. So without loss of generality, I'm drawing my first point at the North Pole. You have that freedom. So we want to add 3 more points, and we want at least 3 points to be in a semicircle. So how many of you are familiar with Dirichlet's pigeonhole principle? Or the box principle? Has anybody not seen the pigeonhole principle or the box principle? Everyone has seen this? Okay. So basically, if you have a pigeon gun, and you load pigeons into your pigeon gun and you shoot them into boxes, okay? No pigeons will be harmed. If you shoot n+1 pigeons into n boxes, what must happen?
2 pigeons are
At least 2 pigeons must be in the same box. So Dirichlet's pigeonhole principle is a phenomenally useful observation. If I draw a straight line down here, I cut the circle in half. I have 3 more points to add. What do you know must happen? At one side must get at least 2. Or it's possible you could keep getting points over here, but that will still count as being on the same side. So if I use the pigeonhole principle, no matter what, one of the sides must get at least 2 points. And therefore you must have at least 3 points in a semicircle. It could be multiple points here or there, but you know that must happen. Question? Or?
So I feel the difference in dimension is like how many points define like a split. Because in like the 0 dimension, the 1-dimensional splits, you get like lines for free.
Yes.
And here it costs 1 point.
So then the question might be, when we get up to the sphere, how many points is it going to cost? So there's lots of ways of looking at this. I think last time I taught this, I said, imagine you start off with, say, 2 points. Each point is going to determine a region where it can have a semicircle. So this point over here will give you maybe something like this. And this point over here will give you something like this. And as long as you choose any point, because we know these 2 points have to be close to each other. Anything in here you win for your next point. Anything down here you lose.
Wait, wouldn't the lines be through the points and through the center of the circle?
Yeah, they should be. That should be the center of the circle.
And they should also pass through the points, right? Because that's like a maximal bound where you can have a hemisphere that contains.
Like the sun.
Like there'd be lines passing through each of the points and through the center instead of like.
Oh, did you get the wrong way?
It seems.
Oh yeah, because I'm right.
Yeah.
I'm drawing it centered at that point. You're right. You're right. Sorry. So let's. So we have something here, and then we want a semicircle going through this. So. Yeah. Right. And then over here, if we take another point, we would have a semicircle going through that. And so then anything in here is going to be a third point that's going to win for both of them. Over here, it's also going to win from both of them. And then over here, it's going to lose. It's close enough to this point, but not to that point. So, right, so this is the region where we lose. Here, we win. Here, we win big, because it works for both of them. Here, we win. So we've got 2 points. So the only way we can lose is if we have 2 points placed in here. But if we have 2 points placed in here, then either one of those points will work. So this is another way to solve the problem with the circle. So the only danger is if 2 points come in here, but then if 2 points come in there. I think the box principle is the better way of doing it. And I think the box principle generalizes significantly better to higher dimensions. One of the dangers, and one of the reasons why I want to give you this proof, is that frequently when you look at a low dimensional case, you might use techniques that are specific to that dimension that don't generalize well. So there was a research problem that I was doing with some students this past summer, and we did the two-dimensional case first and involved a lattice counting. And it turns out that those arguments do not generalize to higher dimensions. All of the expressions we have where we can solve everything exactly completely fail once you get to 3 dimensions. And it took us a while to realize that we actually should scrap the two-dimensional proof completely, solve it in general dimensions, and just completely ignore what we had done. But it was very misleading in that case to look at the low dimensions because we exploited certain facts that we don't have in general. All right. So the next question we could ask here, and as long as we're on the semicircle, I don't think I asked this. What if we want 4 points on the semicircle?
5.
I'm sorry?
5.
So do you think 5 points is going to guarantee 4 points on a semicircle?
Oh, no, I lied.
I don't know. Lying sounds different than you were wrong.
Which is why I lied.
Okay, which is why you lied. So now, what if we wanted to have 4 points on a semicircle? So do we think 5 points is enough?
No.
Okay, do we think 6 points is enough?
Yeah.
People think 6 points is enough? What shape would you like to try to show me that 5 points is not enough? Pentagon. So let's take a pentagon. 1, 2, 3, 4, 5. And then each of these angles is 72 degrees. And so we can see clearly that 3 of these is already going to be more than 180, so we're not going to get 4 points. So the pentagon will fail. And you're saying 6 points will always work. All right, let's try to prove this. Has anybody thought about this, or is this now something that we're all doing new live together? Okay, good. What shape might you want to start with for 6 points? Hexagon. Yeah, so let's see what happens if we do a hexagon. So 1, 2, 3, 4, 5, 6. Oh, things are going to look. So I'll draw a really big center to make it okay. 60, 60, 60, 60, 60, and 60. So you will get 4 points. So do you think we can make this rigorous? That with any 6 points?
Yeah.
Okay.
I don't know if you can exactly call this pigeonhole principle.
Okay.
It's not really.
Okay.
But if you do the same thing as before and you take 1 point, just put it on top,
Yep.
and draw a line through it,
Yep.
then now we need to put in 5 more.
Yep.
5 in 2 places.
Yep.
Means one's gonna have at least 3.
That is pigeonhole.
That is pigeonhole.
Right. So pigeonhole is not just n plus 1 pigeons into n boxes. Basically, if you have p pigeons and b boxes, at least one box is greater than or equal to p over b. And then, given the fact that we're shooting an integral number of pigeons into boxes, it then has to be at least the ceiling of that. So since we have 5, one of the sides has to get at least 3. And that will prove it there. All right, what if I wanted to go to 5 on a semicircle? What do you think it might be?
8.
So the guess is 8. Well, let's see. So if we have 5, we've got 1 here. So now we have 7 more points. And the worst case for us is if it's 4 and 3. So this proves that 8 points will do it. What do we need to do to finish the problem? You have to show that 7 points cannot do it. So what would you look at to try to show 7 points doesn't work?
Wait, but if it's pigeonhole principle, isn't that 7 over 2 ceiling, which is 4?
Yeah.
So
we have we're 1 point here, and we get 4 more here. Yep, no problem. So in general, if I give you n points here, what do you think it is?
N minus 1 over 2.
I'm sorry?
N minus 1 over 2.
No.
Ceiling?
Times 2.
Yeah, I was going to say, you can't have fewer points than n.
Oh, right.
So, we had 8 was going with 5, and then when we wanted 4, was that 6? And when we wanted 3, that was 4? Okay, so it looks like this is increasing by 2 as this increases by 1. So maybe 2n minus 2. So again, to try to figure out what the algebra is, take a few points and try to just get what the pattern is. And so from 3 points here, it looks like 2n minus 2. Is that right? Yes. So I think this argument is going to work. So if we do it like this, we have 1 point here. We now have n minus 3 points left over. I'm sorry, 2n minus 3 points left over. And the worst case for us is 2n minus 1 plus 2n minus 2. Sorry, n minus 1 and n minus 2, sorry. So no matter what, you'll get at least another n minus 1 points on the same side. And so this proves that if you want n points on a semicircle, excellent. And then all you have to do is show that if you have 2n minus 3 points, it fails. So what do you think you should try to show that 2n minus 3 is not sufficient? Yes?
Prove that a regular
Yeah.
2n minus 3 gon will won't have the right
Yeah.
number.
Yeah, so all you have to do is find one configuration where it doesn't work and you're done. And so the natural thing to try is the regular gons. All right, let's make the problem a little bit harder. What if I want n squared points on a semicircle? How many points should I do?
Can't you just substitute n squared?
Yes! It's just 2n squared minus 2.
What happens if we do, like, instead of a semicircle, it's like third semicircle?
Okay, so before that, I just want to get to this for a second. This was just meant to be misleading. When you look at math competitions, when you look at a lot of problems like this, a lot of things in life, if you look at it the right way, it's not bad. Frequently, they will put in stuff that does not matter. And so by writing it as n squared, they're trying to force you, oh, now it has to do with maybe a square number of points. No, it's just some number of points. So remember, all of you, please remember to email me when you make comments in class so that when I have to write letters of recommendation, or when I have the joy of writing letters of recommendation, I can be explicit. I go from this straight to another class where I teach, straight to a meeting. I don't get back to my office until much later in the day when I'm trying to frantically get things done before I have to go get the kids. So always shoot me emails when you make comments in class. What was your comment now? Your question?
What you just substituted.
Yeah, but then you had said something else to look at.
Oh, about like splitting it into thirds instead of looking at.
Oh, okay, yeah. So that's a great one. So instead of saying I want points on a semicircle, what if I want points on a third circle? I mean, half circle has a nice phrase. Third circle.
Quarter circles.
So, I've never looked at this. Have no idea. So this is great. This is a completely new thing. So I want points on the third circle. So, how many points do you think you need to have two? Okay, we all agree that 2 points is not enough because they can just be diametrically opposite. If you have 3 points, do you have to have 2 points on a third circle? I think so.
Yes.
Oh, because they're on the boundaries, yes.
Because remember, if they're just exactly the distance apart, that counts as being on a third circle. It's a closed third circle.
2 points.
I'm sorry?
You said to have
You want 2 points
Oh,
on a
yeah.
third circle. So if you took an equilateral triangle, these 2 points would be on a third circle, and these 2 points would be on a third circle. And so if I start off with this one over here, then this whole range is acceptable. So my next point would have to come in down here. And then once it comes in there, then the next point has to fail. Well, no matter what this is, there's going to be so much of an overlap that your next point is going to have to be either close to this one or close to that one.
Wait, how are you getting so much of a circle from one point?
Because it's a third of a circle, so you get to go a third in each direction. Just like if I give you 1 point on a circle, and I want to be on a semicircle involving this, I can go 180 degrees this way all the way down to here,
Yeah.
or I can go 180 degrees that way.
Oh, but you're saying you'd still have to pick between the two.
You'd have to pick, right. So at this point, I haven't committed as to which is the semicircle I'm going with.
I see.
Once I put my second point down, then I start saying, this is the semicircle I'm building on. So with the third circle, I read that, bless you, with 3 points, we are forced to have 2 points on the third circle. What if you want 3 points on the third circle? So I will make this either extra credit, or you can do this in exchange for other problems that are assigned. And of course, instead of 3, what should really go there? N.
Squared.
Yeah.
Squared.
N squared, yes. Did anybody see the comment I had in the record last year when they interviewed math professors as to what is your favorite number?
Are you going to tell?
I will tell you.
Okay.
I was trying to decide if I wanted to tell you. But
Dramatic pause.
does everybody know the golden mean? So they asked a bunch of math professors, what is your favorite number and why? And I said the golden mean is my favorite number because it has an incredible wealth of remarkable properties, including the fact that it is the reciprocal of its own inverse. How many numbers are the reciprocal of their own inverse? All? And except for 0. So every number except for 0 is the reciprocal of its own inverse. And so you have all of these straight answers from mathematicians as to which numbers are their favorite. And the record did print my answer. I'll be careful because this is being recorded. I'm sure the record understood that it was a joke and just included this for the humor of the readership. But I came up with this when I was in grad school, and I said this with a straight face to my friend who I had the bet on Morley's theorem. He goes, really? And he starts doing the calculation. And then I start running away. But so see if you can fix this. See if you can fix this and find out what it is for third circle. And then, of course, if you can do the third circle. Yeah. So I am the problem editor of the Pi Mu Epsilon Journal. We can absolutely turn this into a problem. I am very close with the editorial process. It's basically me. I will guarantee you that it will be accepted. And so you can then get a publication of a problem in print. You need to be able to solve it as well. But if the class wants to do this, absolutely.
Is there also something there with maybe increasing the dimension arbitrarily?
Yeah, so then that's the other way you can go. So one is to increase the number of points, the next is to increase the number of dimensions, and try to get a sense of how does the answer depend on dimension. So if I want to have 3 points, how does that vary with the dimension? Well then, 3 points might not necessarily be good, because as the dimension gets sufficiently high, you might be able to prevent that from happening. All right, so we don't have enough time to do the sphere. If people want, let me know, and we'll do the spherical case next time. I will leave you with the magic wand problem. So let's see. So let's switch over to this. All right. You have a magic wand, and when you tap the magic wand on the plane, it kills all points that are an irrational distance from where you tap. Only points that are rational distances from where you tap survive. So if you tap once, without loss of generality, where do you tap? Yeah, might as well tap at the origin. So if you tap at the origin, what's left?
All rational numbers.
All rational numbers, yes. More than just all rational numbers, though. It kills anything that's an irrational distance from where you tap. Concentric circles. Be more specific. Which concentric circles?
All irrational distances.
Right. So basically, this is not even closely drawn to scale, but every circle with a rational radius survives, and everything else is killed. What do you think my question is?
How many tabs?
How many taps to do what?
Kill everyone.
Good. So, how many taps to kill everyone?
Wow.
This is like how many licks does it take to get to the center of. Do you guys know that commercial?
Yeah.
Yeah. So, is it possible? First of all, is it even possible? Maybe it's not possible. Maybe there will always be something that survives after finitely many taps. So the first question is, prove that you can kill everything in the plane with finitely many taps. Then, if you can do that, find a bound for that. And then, if you can do that, find the best bound, find the actual answer. Yes?
Wait, so after one wave, does it compress everything?
No, so after one
space?
wave, you just have circles of rational radii that are left, nothing else.
And you're not allowed to move.
You can then move, and you can tap any way you want in the plane.
Oh, I see.
You are God. Okay, you are at the board level like this, and you come down and you choose where you want to tap. Did anybody ever watch the old Tron movie?
Yeah.
The scene when they're playing with the thing and you have the rings around them and it hits. I'll try to send you the clip from Tron. People want that's now a valid movie night. We can't show movies in general without paying fees. But if it is worked into a class,